Hello. In this session, we discuss the applications of bio and Savart. There are two applications. One, magnetic field at a point at the center of a circular loop carrying steady current. Now, why steady current? It's very important that if the current is varying, we cannot determine a constant value of magnetic field at that point, because according to bio and Savart law, the magnetic field strength depends on the strength of the electric current. So to get a single equation, we have to consider steady current in all the discussions. Okay. Now this is a circular loop carrying steady current, and a current I. The steady current I is entering and flowing in the anti-clockwise direction. And these 2 points are very close to each other, therefore we can consider this to be a complete circle. Now, to apply bio and Savart law, we have to consider a length element. So I consider a length element dl over here, and from that dl to the point that is at the center of the loop, the distance is a. But that distance a is effectively the radius of the circular loop. Now another point to be noted is that the angle between the direction of flow of current in the dl and the line joining the point is found to be exactly 90 degrees. That means here the angle theta is always 90 degrees wherever you consider the length element dl over the circular loop. And the distance from the length element to the point also remains the same throughout. That means R equal to E throughout. Alright. Therefore, how to find the total field at this point due to the whole circle? Using bio and Savart law. Now, according to bio and Savart law, we have the small magnetic field due to the length element dl carrying current I is found to be equal to mu 0 by 4 pi into I dl sine theta by r square. This is the basic formula of bio and Savart. Now into this we substitute the condition here. Here we understood that theta equal to 90 degree all through and r equal to a. Therefore, we have dB equal to mu 0 by 4 pi into I dl sine 90 divided by a square. Now, the value of sine 90 is 1, therefore you can take this to be 1. So you get dB is equal to mu 0 by 4 pi into I dl divided by a square. This is the strength of the magnetic field at this particular point due to this length element carrying current I. Okay. But the question is, what is the field at the center O due to the whole circle carrying current I? So for that, we have to consider next linear. Like that, as you go on splitting the circular loop into small numbers of large numbers of dls, you will be finding the magnetic field due to each dl carrying current all through the circular. This is what the procedure is. But that process is very tedious and we will be looking for other mathematical applications, the simple one, to get the whole field. Now as you see, the length element is getting added all through. You are actually integrating the magnetic field due to each dl over the whole circle to get the what you call the total field. So the process of integration must be applied to this to get the field due to the circular loop. Okay. Now for that, applying integration, we see total field B at that point will be equal to integral dB, that's equal to integral mu 0 by 4 pi into I dl by a square. Now as you do the integration, there will be limits to be applied, because you are starting from this particular point, that is 0 of the length, and from here as you move through this much distance, that is your length dl. So like that, when you go for the next dl, you are getting dl added to the previous one. When you go all around, you will be taking the dl to be added, and you are starting that dl from 0, and as you go once around, you will be getting the whole length of the circumference, and therefore the upper limit must be 2 pi a. So integral 0 to 2 pi a is the limit of your integration, provided mu 0 by 4 pi I a square. All these quantities are constant for the figure. Only dl is the variable, that dl varies from 0 to 2 pi a. Clear? Now, doing the integration process, after doing the integration and all, we get the magnetic field strength B will be equal to mu 0 by 4 pi into mu 0 by 4 pi into 2 pi I divided by a. This is the formula we are getting for the field strength at the center of the circular loop. Direction, that depends on the direction of flow of current. Okay. Now, this is all needed for your board exam. After showing the integration, the final result is in F. Okay. Now, let us see the other things relating to what is the direction of this magnetic field. If the current is flowing in the anti-clockwise direction here, you will be holding the conductor like this. Suppose I consider a length L here and I am holding it like this. So the magnetic field is going around like this. Okay? All around it is coming like this. So at the point O, the magnetic field will be coming towards you. Okay? So if the current is anti-clockwise, then the direction of this magnetic field will be perpendicular to the plane of the board and towards you. So if it is clockwise, what happens? The direction will be into the plane and away from you. Okay? Now this is all about the field strength in the center of the circular loop carrying current. Now suppose this circular loop is having n turns, means n number of turns for the loop. Now each turn will be having a current I flowing through it, because current is flowing very fast, that it is not starting from here and slowly moving around and all. No. As you switch on, the current will be present at the very instant in all the n turns. So the effect of the current will be n times I, if you have n number of turns instead of 1. Therefore, in that case, the magnetic field B will be equal to mu 0 by 4 pi into 2 pi n I by A. You get 2 pi n I by A. That means n times the current is. So if it is a single circular turn, this is 1. And if there are n number of turns for the circular loop you consider, then this will be the equation. Current is getting multiplied n times. Okay? This is all about the first application.